SwayamPrabha. Digital India. Educated India.
Hello everyone, welcome to the first lecture in Interfacial Fluid Mechanics. In today's lecture, we'll be covering two key topics. What are the relevant non-dimensional numbers that one would normally encounter in interfacial flows? And then we'll look at the notion of Laplace pressure. Let me write down both of these points. We'll be looking at relevant or common non-dimensional groups. And then we'll be looking at the notion of the Laplace pressure. So to illustrate what are the non-dimensional groups that one would encounter in interfacial flows, let's actually start with a problem in conventional fluid mechanics. Now, the problem of interest to me in this particular case is of a solid particle. Let's say it's a spherical particle. So it's a problem of a moving solid sphere. Now, this solid sphere could be settling in gravity. So there is gravitational force here. And let's say the particle size is A. It could be the radius. And it's moving in a fluid or a gas whose viscosity is mu and density is rho. Now I could be asking, what is this? What is the drag force? Drag force, what is it as a function of the particle size, gravity, density difference? So let's say the density of the particle is rho s, and the density differences are the densities, viscosity, right? Now, if I were to look at the free body diagram of this particle, here's the particle. If the particle is moving downwards, it's experiencing a drag force and it's experiencing a weight minus a buoyancy force. Okay. Now, if the particle is moving with a velocity of u, I know that at steady state, the drag force will be equal to the weight minus the buoyancy force, right? The velocity of the particle itself would be a function of the differences in the density, the size of the particle, and gravity. So therefore, this expression that we had here can be replaced with a drag force would now be a new function. Let's say this is f prime of particle size, velocity, density, and viscosity of the particle. Now, if I use Buckingham pi theorem, I'll assume that all of you know Buckingham pi theorem. There are several good textbooks in fluid mechanics which explain Buckingham pi theorem. Now, if you use Buckingham pi theorem, there are 5 parameters here, right, and 3 dimensions, and therefore I get 2 non-dimensional groups. Here 3 dimensions are mass, length, and time, and therefore I have 2 non-dimensional groups. I'm not going to derive the Buckingham pi theorem or how to determine the relevant non-dimensional groups in this particular case. I will directly write what are the non-dimensional groups. I can now have a relationship between one non-dimensional number and another non-dimensional number. One of the non-dimensional numbers that is of relevance to us in this particular case is a drag force divided by half rho u square times some area. Okay, this is a non-dimensional number, and the other non-dimensional number would be pi 2 in this case, would be the fluid density, the velocity of the particle, the size of the particle, and the viscosity of the surrounding fluid. So now you can actually clearly see this. The left hand side here is usually referred to as a drag coefficient, and the right hand side is the Reynolds number. So what do we learn from this? We see that the drag force is a function of the Reynolds number. Now, even without doing all this analysis and starting from Buckingham pi theorem, I can make a guess that the only relevant non-dimensional number, fluid non-dimensional number which will matter for this problem is the Reynolds number. The reason for that is, if you look at the motion of the particle, when the particle is actually moving downwards, the fluid is moving upwards. Now there are two forces at play. For the fluid, one is inertia of the fluid, and the other is viscous forces. So I can straight away think of a non-dimensional number such as the Reynolds number, which is the ratio of inertia to viscous forces. Right? Now let's contrast this with a moving droplet. Now, unlike the case of a sphere, a moving droplet need not be perfectly spherical. I've shown here it to be a sphere, but in general, it can actually be a deforming sphere. The surface of the sphere can change its shape, and let's say there is an effective characteristic length of size A, which characterizes this droplet. Okay. We also have a new force, we'll call it as gamma. This is the surface tension force. The other parameters are the same. We have viscosity of the surrounding gas. We have gas, and we have density of the surrounding gas. Similarly, we have density of the droplet. We also have viscosity of the droplet. There is a gravitational force which is making it settle down. So let's now write down what will be the drag force on this in this problem. The drag force now is going to be a function of all these parameters, the two densities, density of the droplet and the density of the surrounding medium, the viscosities, and then surface tension force. And you can also have a velocity that is imparted to the particle or the droplet, and the typical characteristic size of the droplet. Okay, so straight away you can imagine that if you count the number of parameters, if I call this drag force as D, then I have number of non-dimensional groups there'll be 8 parameters I have, okay, and 3 dimensions, mass, length, and time, and therefore I have 5 non-dimensional groups. Okay, now I can straight away guess a few non-dimensional groups. I could think of, let's say, a drag coefficient would be something like the drag to half rho u square times a square. But I could think of very simple non-dimensional groups such as the density ratio, I could think of another one, which is the viscosity ratio, the ratio of the droplet to the surrounding viscosity. And now I want to determine what are the other non-dimensional groups. Now, if you notice here, except in the drag force where a velocity is entered, the other two non-dimensional numbers do not have a velocity, nor they have viscosity, nor surface tension, right? So how do we think about other non-dimensional numbers? Now let's look at the forces at play. We can approach this problem from Buckingham pi theorem and determine various possible non-dimensional groups, but I want to try to tell you a more intuitive way of arriving at guessing the correct non-dimensional numbers. So the first one, what are the forces at play? We have inertia, we have viscous forces, we have surface tension, and it's also possible that we have gravity. Okay, now I can come up with various combinations of these forces such that I can come up with non-dimensional groups. If I think about inertia and viscous force, I have the Reynolds number. This is inertia to viscous force. But I could also have inertia to surface tension. If I can come up with another number, this is usually referred to as the Weber number. This is inertia to surface tension. We could even have viscous forces to surface tension. This is referred to as the capillary number. And finally, we could have another non-dimensional group, which is surface tension to gravity. This is referred to as the bond number. Right? Or gravity to surface tension. That's usually the other way around. Let me just correct that. It's usually gravity, its bond number would be gravity to surface tension. Remember, these are all non-dimensional groups. Now, this is not the only possibilities. We have inertia to gravity that I can also write. Let me highlight that here. This is referred to as a Froude number. So you see here, just by addition of surface tension, we have seen new non-dimensional numbers. We have the Weber number, which should measure the ratio of inertial forces to surface tension forces. And we have capillary number, which should measure the ratio of viscous forces to surface tension. Okay. And then we would also have, if gravity is an important force, then we also have surface tension to gravity. Now, why would surface tension introduce new forces? Now I can imagine that if I have a droplet which is perfectly spherical and the moment I subject it to an external force, this could be a drag force from the surrounding gas, the droplet need not be in its spherical shape anymore. It could actually deform. Now surface tension, as we know, tries to bring it back to a spherical shape, whereas another force such as inertia could actually allow it to deform. So now I could actually have a combination of balance of forces. A viscous forces could be deforming the droplet, whereas a surface tension could be trying to restore the shape of the droplet. So therefore, in such systems, we actually not only have an additional force, but we could even have very interesting behavior such as oscillations, where we have two competing forces constantly exchanging their strengths. And therefore, one of the common things that we'll encounter in interfacial flows or interfacial fluid mechanics are waves. Okay, and some of these waves are referred to as capillary waves. We look at them more closely later in the course. Now, let's look at, in this particular case, I'll take a spherical droplet. In today's lecture, what we saw is we looked at the relevant non-dimensional numbers that we would encounter. So we have not derived these non-dimensional numbers from any governing equations. We have not encountered them directly in any governing equations, but we quickly looked at a problem of a moving droplet, and we looked at the forces at play. Okay, and we saw that there are several forces at play: inertia, viscous forces, surface tension, and even gravity. And if I take the ratio of these forces, I can come up with various non-dimensional groups. These are not the only non-dimensional groups. Sometimes you may have additional non-dimensional groups that may also be defined. For example, I can think of a number called Onasage number. We will encounter that later. Okay, and also notice that all these numbers are not independent of each other. For example, if I know the Reynolds number, which is the ratio of inertia to viscous forces, and I know the Weber number, which is the ratio of inertia to surface tension, then I can straight away obtain the capillary number by just taking the ratio of Weber number to Reynolds number, right? So these are not independent non-dimensional numbers. If similarly, Froude number, Bond number, and Reynolds number can again, all these numbers can again be related. Weber number can again be related. So we will encounter these different various numbers when we actually start working with equations, and when we non-dimensionalize these equations, some of these non-dimensional numbers will naturally emerge. And then we looked at the notion of a Laplace pressure. So just to quickly recap, what is the notion of Laplace pressure? What we are stipulating is a bubble or a droplet, which is having an interface, which is an interface between fluids A and B, and there is a surface tension at this interface, which we refer to as gamma AB. Now, I may sometimes refer to surface tension as just gamma without any subscripts AB or 1, 2, if the context is obvious. In this case, I'm trying to reiterate that this is a surface between A and B. So I have gamma AB. Now, and intuitively, we would expect surface tension to minimize the surface area, the surface energy. This connection between surface energy and minimization process is something that we'll be looking at in a few subsequent, after a few lectures. Now, in this particular case, what we studied is we looked at what is the amount of work that is needed to change the radius of the droplet. And if we claim that the system is in equilibrium, which means that the droplet or the bubble does not change its radius anymore, at its equilibrium, the pressure inside the droplet or a bubble to the pressure outside is related to, the difference in the pressure is related to surface tension and the radius. And if I say that the surface tension, if the pressure inside, if I call it as P inside and the pressure outside is P outside, then we also notice that the pressure inside is higher than the pressure outside. This is also true for a soap bubble, which could be made up of two interfaces, albeit a very thin interface. The pressure inside can be twice that of a bubble or a droplet. Okay. Now, the pressure jump can be twice. Okay. And this is exactly because the pressure inside is higher than outside. This is exactly the reason why soap bubbles, if you make a soap bubble, the soap bubbles burst, because they burst violently, and it's a very, very fast process. They burst violently just like a balloon would burst, because just like a balloon, the pressure inside is actually higher than pressure outside. So, and then we'll be looking at governing equations that govern fluid flow, especially interfacial flows, in the next lecture.